All right, guys, so we ran out of time to cover examples 6, 7, and 8 in class. I think you have a sufficient amount of knowledge to do these, but if you wanted to refer back to these and just get a little more supplemental instruction, here we are. So let's look at example 6, part B. So they want you to take the integral here. The integral here, and they want you to write it as a Riemann sum where the limit as n approaches infinity of the number of rectangles is going to cause it to give you the exact area instead of the approximate area. So let's do that. So in order to do that, in general, right, so for the Riemann sum, we've got this one over here for part A. We've got some things I want to point out here. So we've got limit as n approaches infinity. That allows the Riemann sum approximation to actually become an exact value of the area under the curve. We've got the width of each rectangle multiplied by the height of each rectangle. The height of each rectangle is obtained, if you guys remember in class, we actually found the x value of the rectangle, and then we evaluated it using the function f, right? So in this case, the function was 3x squared minus 1, so we took the value of x sub k, which was this, and we plugged it into f of x, and we got this right here as a general expression for the height of the kth rectangle. Okay, so let's do that with this one here. So the width of each rectangle in our scenario, we are covering a distance of 0 to -2, so that's a distance of 2, and there are n rectangles. So the width of each rectangle will be 2 divided by n. Before we talk about the height of the rectangles, I think it's helpful to talk about how to express x sub k as a function of k. So in other words, how to find the x coordinate of the kth rectangle. So if you want, let's say you have a million rectangles and you want to find the height of the 12th rectangle, we're talking about x sub 12 here. So let's make a formula that would quickly give us the height. Not the height, the x coordinate of that rectangle. Then we'll plug that into f to figure out the height. Okay, so x sub k, as a general rule, can be found by saying it's a plus the width of each rectangle times however many rectangles you've been through, or whichever one you happen to be on here. And this is for a right Riemann sum. Okay, so in our case, the starting place here for A is -2. So the x coordinate of any kth rectangle is going to be -2 plus the width of each rectangle times k. Okay, so we can simplify this into -2 plus 2k over n. And that would give us the x coordinate of any rectangle. So we're going to use that here now to figure out the height of each rectangle. So the height of each rectangle is going to be the y value when we evaluate at the x that we are interested in, which we just derived right here. Okay, we just figured that out. So this is going to be f of x sub k. So x sub k is -2 plus 2k over n. That's going to give us the x value, and when we plug that into our function, what was our function? So our function says to add 3 to the input and then square the result. So we're going to add 3 to this input here, and square the result. So what do we get when we do that? So we get -2 plus 2k over n, add 3 to that, and then square the result. Okay, so let's simplify this a little bit. -2 plus 3 is just 1. So let's call this 1 plus 2k over n squared. Okay, so I like that. That's f of x sub k. So that's the height of your rectangles there. So let's add them all up. You ready? So we're going to take the limit as n approaches infinity, because we want to get the exact area here, of the summation starting at 1 to n of the height of all these. So that's our 1 plus 2k over n squared. That's our height times our width, which is 2 over n. Sometimes the 2 over n will come out in front of the summation because it doesn't have a k in it. That's fine if you want to do that. I'm just going to leave it right there. Doesn't really matter. Just depends on which textbook you consult or who you talk to. On this, what I would do for finding the value here is I would just use my calculator and run this. You can also use Wolfram Alpha, WOLFRAM alpha.com. And you can just ask it to compute the integral from -2 to 0 of that function there. And it will do it for you. Okay? All right. So we'll let you guys do that. But if you care, this one is 26/3. Okay, let's do one more of these, and then we will go down to this section here. So third period, you guys did not get this far. 11th period was able to do one of these, but I'm going to do another one here. And then we will go to the back page here. Okay, so how about this one? So a trig function, sine of x. We're going to integrate area under the curve from 0 to pi. So if you imagine sine of x looks like this on that interval from 0 to pi. So we're going to find the area under the curve there. So that's pi right there. Okay, let's do it. So what are the widths of each of our rectangles going to be? So it's going to be the total horizontal distance divided by the number of rectangles. So that distance there is pi, right? Pi minus 0 is pi. So it's going to be pi over n because there's n rectangles. If we want to talk about the kth x value of the kth rectangle, it's going to be a plus delta x times k, which in our scenario is going to be 0. A is 0 because we're starting here at 0. Plus delta x is pi over n times k. So in general, x sub k can be given as, I'm going to call it pi k over n. So then the height of our rectangles here is going to be f of x sub k. And in particular, for this specific scenario, f of x is sine of x. So that's going to be sine of x sub k, which is pi k over n. So that's going to be the height of our rectangle. So let's put it all together. You ready? Limit as n approaches infinity of the summation from 1, I got a lot of alarms going off today, sorry. 1 to n of sine of pi k over n times pi over n. And if you remember, the area under that curve there is 2. So, all right. Let's move on to one of these. So these are backwards. So what we've done here is we've taken the integral and we have gone to the Riemann sum, summation notation. What they're going to do now is they're going to give you the Riemann sum and ask you to go back to figure out what the integral is that would match it. Okay, we did this one in 11th period, but I'll do another one here for you if you are a little confused on this. So we're just working backwards here. So the first thing I notice here is this is the width of our rectangles here. It's 2 over n, which means this tells me that the width of our interval, so the width of our interval is 2, right? Because that right there, that tells me that, whatever our function is, I have no idea what the function is, but let's say it looks like this. If we have a distance here of 2, that means that the width of each rectangle will be 2 divided by n. So, okay, so the width of our interval is 2, so that's helpful to know. Let's look at this part right here now. So this to me, so this is f of x sub k, right? That's f of x sub k. So in general, it looks to me like f of x, the rule here is to take 3 times the input, this is the x value, right? And then add 4 to it. So it looks like the function here that we are going to be integrating is 3x plus 4. Now, this is a little confusing here. How do we take this and make that look like, so that's x sub k, right? X sub k is 2k over n minus 2. Let's work our way backwards, right? Remember what we just did? So we got down to here, right? We got down to here, and then we need to go this way to figure out what we started with, right? So we can figure out our a value. So let's do that. So let's work our way backwards. So I'm guessing probably this was -2 plus 2k over n, which was -2 plus 2 over n times k. So now the picture is starting to become a little more clear here. This is our a value. Delta x is 2 over n, which we already knew that because that's over here. So our a value here must be -2. So we must be starting our integration here for this function at -2. And the width of the interval is 2 then. So if we start at -2, that means we're going to go up 2 to 0. And then we're going to say this must be 3x minus 4 dx. Okay? Sorry, plus 4, not minus 4. Plus 4. 3x plus 4. And then if you are curious, you can just throw that in our calculator and have it calculate that for you. But that is going to give you an area of 2. Okay? All right, let's flip over to the back page here if you're curious. And let's do C here. So for C, it's looking to me like I can write this as 1 over n times pi over 6. Okay? So it looks to me, how do we say this? So delta x is pi over 6 times 1 over n. So really the way you can think about this is pi over 6 over n. That's the same thing. So our interval, the width of our interval here is going to be pi over 6. So pi over 6 is going to be the width of our interval. Okay, all right. And then now we need to come in, and this is our function right here. So it looks like a pretty basic f of x is going to be cosine of x sub k. So this right here is x sub k. So that means we need to kind of think our way backwards here. So if x sub k is k pi over 6n, maybe the step before this we had pi over 6 times 1 over n times k, which the step before that, maybe we think of this as pi over 6 over n times k. This means that our a value must be 0, right? So this is going to be a plus delta x times k. Obviously, k is right here. Delta x is pi over 6 over n. So our a must be 0. So we must be starting at, in this scenario, a must be 0. And then our delta x is pi over 6 over n. Hopefully you see that that and that are saying the same thing. If not, come ask me and I'll help you. All right, so our integral is going to run from 0 to pi over 6 because that was the width of our interval. Our function here is going to be cosine x dx. And if you're curious, the area under the curve there is exactly 1/2. Okay, all right. So you're going to run into some tricky ones that might, let's say, don't look at this yet. Don't look at that. But what if you came across this, right? So what they're saying here for number 8 is a Riemann sum in simplified form should be unsimplified before being translated into a definite integral. So what you might have to do is you might have to do a little bit of algebraic gymnastics here to get this into a form that resembles the height times the width, right? Like in general, we know that the width is going to be something over n for these. And, if you have k cubed over n to the 4th, you could say, all right, look, so that's k cubed over n cubed times 1 over n. And, oh, look at this. This happens to give me the width that I want. So therefore, this must be the height, right? So that must mean I must be taking k over n and cubing that, right? So it's a little bit of gymnastics to make it work, but, you can do it. It's possible here. Okay, all right. So what we need then, I think the best way to describe this to somebody is to say, look, your goal is you really want this 1 over n or something over n to pop out here, okay? So your goal is to get something over n to pop out. In this scenario, it's 8 over n down here, so that's helpful. This is going to be tricky. We're going to have to pull a 1 out of n out of all of those. For this, we have to ask ourselves, how can we get root k over root n cubed to be, how can we get a 1 over n to come out of this? So let's manipulate this so we can get a 1 over n. I'm going to say that if you take the square root of n cubed, you actually get n times the square root of n. And here's your n that you need. So just say, hey, look, this is root k over root n, right? And then times 1 over n. That's where this n comes from, that 1 over n right there, okay? So now I'm here. I can work with that. That, to me, that looks like the square root of k over n times 1 over n. And so let's see. Okay. Trying to think of how how to explain this. All right. So what we want here is we want square root of k over n. So it looks to me like our function here is f of x is equal to square root of x, right? And x sub k is k over n, which is really 1 over n times k. So it looks to me, right, 1 over n times k is really our a plus delta x times k, which means what? That means our a value here is 0, and our delta x is our 1 over n, which we kind of already knew that. So basically what we're saying here is we've got, our integration is starting at 0, and it's going up, what would b minus a be in this case? So I'm going to say it's 1. And we know that the width of the interval, sorry, people are texting me here. The width of the interval is going to be whatever you're dividing by n. So it's the width of the interval is going to be 1 there. So that means from 0, we're going to go up 1. And then our function here is just the square root of x. And then dx. And if you are curious to know the value of that, it is exactly 2/3. Okay, so these get a little tricky. You gotta do some serious algebra gymnastics to make these work. Okay, all right. So how about this one? So we got to we need to pull an n out of the bottom of these. So if we pull an n out of the bottom of these, what would we have left if we factor an n out of the bottom? So the tops are going to stay the same. You're just going to lose a power of n in the bottoms here. Okay, so this is going to be n squared. This is going to be 9 over n squared plus n squared over n squared, right? So now, as a general rule here, what are we saying here? So this is our first rectangle, second rectangle, third rectangle. How do we, 1 maps to 1 here, first rectangle, second rectangle maps to 4, third rectangle maps to 9, n rectangle maps to n squared. So the idea here is to get the output, what we've got here is we've got our k, whatever number we happen to be on, over n, and we are squaring that. That's how we're getting these terms right here, okay? The width of the interval is 1 over n, so 1 over n. So that means, if we're going to do our summation here from k equals 1 to n, and we take the limit here as n approaches infinity, this is what we're working with, okay? So our x sub k is k over n, right? So let's work backwards. That looks a lot to me like 1 over n times k, which looks a lot to me like 0 plus 1 over n times k. So our starting value for our integration then is 0 right there. Our width of our interval is going to be 1. So we're going to go from 0 to 1. And it looks to me like all we're doing is x squared for that function. See how it's x sub k, k over n is being squared there. So our function is just going to be x squared. Don't forget the dx there. And then your exact value here. I would show you how to do it on the calculator, but for the sake of time, I'm just going to tell you it's 1/3. You can do it on your calculator. All right, and then finally, let's look at C here for number 8. So first thing I notice here is that the width of our interval is going to be 8. And something that I noticed that is really interesting is that we have 16 over n instead of 8 over n there. So that, tells me that something's getting doubled in there, right? For us to finish with 16 over n instead of 8 over n means we're getting doubled there. So let's actually go through and figure what is up with this right here. So we've got 1 plus 16k over n. Remember, x sub k is the starting bound plus delta x times k. And in this case, we actually know that delta x is 8 over n, right? So we know that this is 8 over n times k. And what's happening here is that you've got a plus 8 over n times k, and we're doing something to that. We just don't know what a is. We're going to figure it out here in a minute. We're doing something to that, and we're finishing with 1 plus 16k over n. So the question is, like, what do we have to do to this? Like, what does that a need to be for this to turn out to be 1 plus 16 over n times k? And what I want to do is work backwards here. So what I want to do is pull out the 8 over n. So for me to make this look the way I want it to look, I'm really trying to get to this right here, okay? That's my goal. I'm trying to make this look like that, okay? So we're going to work our way backwards. This step, I can pull the 2 out of this because to get to 16, you had to multiply 8 over n by 2. Now, the problem is that this and this are not matching in the way that they're supposed to be matching, right? So what we need then is we need to get rid of this 2 because you can't just double the delta x here, right? For us to find the x coordinate of the kth rectangle, it needs to truly be delta x times k here. So what we need to do is we need to pull this 2 out. But before we do that, this is going to seem really weird. I'm going to add 1 to the front here, and I'm going to subtract 1 on the back end, okay? It's going to seem really weird, but bear with me. When we do that, we get 1 plus 1 is 2 plus 2 times 8 over n times k, and then don't forget that minus 1 at the back end there, okay? The whole reason I did that 1 there was so that I'm going to divide by 2 here, and I want that 2 to disappear, and I'm trying to not leave with a fraction here. So when we do that, if you factor the 2 out of this, working backwards here, what do we have? So we pull the 2 out, and we're left with 1 plus 8 over n times k, and then minus 1. Don't forget the minus 1 at the end there, okay? This is looking really great now because basically what we have here is we have our a plus delta x times k. So this is our x sub k right here. This is our x sub k right here. It's this little guy right here. It's that whole thing, okay? So it looks to me like the function inside the natural logarithm, there's actually a composition of functions going on here, is we have ln of 2x sub k minus 1. It looks like that's what we're actually doing here. Okay, so it looks like ln of, basically what I'm saying is 2x minus 1 is the function there. And our a value, our starting value is 1. So we're going to integrate from 1 to, the width of our interval was 8. So we're going to go from 1 to 9 of ln of 2x minus 1 dx. And if you throw that into the calculator, you're going to get 16.0823. Okay, that one is tricky. That one took quite a bit of algebraic gymnastics to make happen. But that is the nature of calculus. Sometimes we have to do really ugly math like that to get it to work and make it look the way we want it to look.